All right, so today's topic is clustering. Clustering is very different from classifiers and regressors. The clusters solve a completely different problem. And clusters are your introduction to something called unsupervised learning. So let me mention this. There's some descriptors to it. Clusters are unsupervised learners. What does that mean? It's a rather old term, supervised versus unsupervised. And the industry, it has stuck to the industry, though the meaning is, I suppose, supervised. Unsupervised learners. What does that mean? Now you realize that for supervised learning, the X vector goes in, and what comes out is Y hat, isn't it? And the data, so this is supervised learning. Could you guys give an example of supervised learning that we have learned so far? What are some supervised learners?
Cows and ducks.
Oh, yeah, yes, that's an example. Classifiers and regressors. Those are your classifiers, regressors. The defining quality is you have to give a training data which contains the x1, x2, x3, etc., etc. And then you also have to provide what does it map to? What is the target value? Right? So the training data gives you a mapping from the input space to the output space. Output space is the Y space or the target space. And so all of supervised learning is to learn a function Y is equal to some function fx, right, plus epsilon. This fx is close approximation approx to the ground truth. The ground truth that generated the data. So this data that you have that generated the data. So I hope this is a summary of what we have been doing. Classifiers and regressors. In the case of regressor, you're trying to predict the sale of ice cream on a beach. Well, you need some data. You need, for a given temperature, for a given wind speed, for a given day of the week, how much ice cream, what is the historic data? How much ice cream did you sell? And one can use that now to create a function that generalizes the behavior between input and output, learns the relationship or learns the function f, which provides you a generalization. On the other hand, unsupervised learning has a completely different goal. Unsupervised learning, there is only the x vector. Only we only get the entire data space, and there are no target variables. So these are unsupervised learning examples. So I'll explain to you what that means, because this seems pretty mysterious. How can you just get a data set that gives you the input and there is no output? So the way you think in unsupervised learning is you do not think in terms of input and output. You say there is data and there is some pattern in the data. You have to recognize the pattern. So one word that you may use for unsupervised learning that I think would be good is pattern recognition. And I always think of it like that. This is pattern recognition. The goal is to recognize some pattern in the data, whereas the goal in predictive modeling is predictive modeling. So in supervised learning is predictive modeling. So you will often find textbooks in machine learning since machine learning has become such a vast field, we just we just deal with either unsupervised learning or supervised learning. So there are entire books devoted only to predictive modeling, namely classification and regression, and some things in between, like semi-supervised, like recommended systems and so forth. And there are certain books which are related only to pattern recognition. It says, give me the data and we'll find some patterns. And I'll give you an example of what those patterns are. And why is recognizing pattern in the data a form of learning in itself? We'll come to that in a few moments. Now, consider this example. And so I'll just mention some examples of pattern recognition and then I'll explain them. Clustering, dimensionality reduction. Later time and so forth. Anomaly detection, anomaly and outlier detection. These are examples of pattern recognition. So today we are going to, and I'll explain what those are, but at some point today, but today we'll start with just clustering. What are clusters? So this is the scope of things. So typically books call this clustering, and sometimes people call these topics or the things that do it, the algorithms that can do it, as clusterers, just like classification and classifiers are there. So what is this topic, clustering and clusters? To illustrate this, imagine that you are looking at this data. Let me create some data points for you. Are you guys able to see the data on the screen?
Yes.
Suppose you see data like this. And I've simplified it. What do you see data? What can you recognize about the way data is distributed in the feature space? Let's say that this is your feature space. This is X1. This is X2, right?
There are two distinct clusters.
Yes. What you notice is that data is not uniformly spread in the feature space. It tends to be centered around these two clusters or chunks. There are two chunks or clusters of data. And recognizing these clusters in the data space is one of the core goals in machine learning, because you see pattern in the data and that pattern means something. For example, if it is a medical situation, one cluster may represent people who are healthy. If you have done some lab work and there are certain biological metrics, biometrics, then the other cluster might represent markers or may signify people who are healthy, and another one may signify people who carry a particular disease. So data tends to segregate itself out like this. That would be an example. Or take the example of this. Suppose you are a person who's never been to San Francisco, and somebody just drops you in San Francisco in the middle of the night or at night, or maybe even in the daytime. You feel completely lost. Well, let's assume that you don't have Google Maps. You feel completely lost. And what do? You start taking a notebook and you start walking around the streets and keeping track of which street intersects which street. And suppose I tell you that I drop you in some area and I say, go find yourself a good restaurant to eat. You're hungry. Generally, it's very hard for you to determine which direction you should go in order to find food, or the restaurants or things like that. You don't know where the residential areas are, you don't know where the parks are, and so forth, because you have a very local view of the city. But suppose now that you are flying over San Francisco, and we all do that when we arrive on flights into the San Francisco airport. We often see the whole city lit up or in broad daylight. You see, and when you see the city, what you see are very specific patterns. You notice that the financial district, all the commercial buildings are, a large number of them are clustered around the financial district, the waterfront, isn't it? The tip of the peninsula. You also notice that there are residential areas slightly back into the peninsula, deeper into the peninsula, and towards the waterfront, towards the sea. And then you notice the Golden Gate Park. Lots of greenery, lots of trees, which are all clustered together. So when you see these clusters, I suppose if I were to oversimplify San Francisco, you would say it is like this. This is the Golden Gate Bridge. Bridge. And obviously, this is an oversimplification. You would say that the financial district seems to be something like this. This is the financial or commercial area. Then you realize that there is a lot of greenery, which I'll just oversimplify and make it like this. Greenery, trees. Let's call this the Golden Gate Park. And then you see there's houses. And you see those houses. And you see that the houses form, roughly speaking, a region of their own. This is a very rough approximation of San Francisco, but would you agree that this has some semblance to what it is? Isn't it, guys? And so suppose you're looking for, you're dropped in some place and you have to go find your aunt or your best friend who lives in a house. And let's say that we drop you right at the Golden Gate Bridge. Suppose this is where you are dropped. Sorry. What just happened? Give me 1 second. So guys, this has crashed. So let me yeah. Suppose you're dropped at this location, the Golden Gate Bridge, and you want to go to the park. You know where to go or how to go. If you have to go to the residential area, you have an idea of how far you have to go to reach the residential area to get a sense. So in other words, recognizing patterns about a city has a lot of practical value. It's a form of learning because it expedites or it facilitates a lot of things you would want to do with the data. Are we together, guys? So this is the purpose of finding patterns in data. In this particular case, finding clusters in data. So we will limit ourselves to clusters, but then it raises the question, how do we know, does data always come clustered? It may or may not come clustered, right? So for example, it is perfectly possible data won't be clustered. So you could have a situation in which data is all like this. Things like that. Huh? So this is your rather homogeneous, mostly lacking in clustering, mostly lacking in clusters, isn't it? You can't discern or you can't see any well-defined clusters in the data. And sometimes it is so. For example, if somebody has just combed the beach, the sand on the beach, it's all uniformly set in a box, in a child's play box. You don't see clusters of sand. But then after some time, children come and play. And once they are done playing, what you notice is, or as they play, you notice that all sorts of sand hills are being created. Clusters of sand are being created, isn't it? So, so it raises the question that when we look for clusters, how often do we find clusters in data? Right? So those of you who are new, I want you to guess most of the day, like how often do you find clusters in data sets? So imagine the space of a million different data sets, something to do with automobiles, something to do with atmosphere, something to do with health, financial data, astrophysical data, right? Chemical data, social data, political data. How often do you find genuine clusters in the data? 10% of the time, 12% of the time, 1% of the time. Could some of you who are new to this class give me a guess?
I would say 10% of the time.
So you think approximately how often do we see clusters? So let me pose this question. Clusters. Let's say 10% of the time. Anybody else has a different guess?
Say 98.
98. Somebody says 98% of the time. Dennis.
100% of the time.
100% of the time. Anybody else?
70.
70% of the time. Anybody else, guys? So I'll give you the interesting thing about nature, and it has to do with the way data is generated. It's in fact a very fascinating subject that relates to things like chaos theory and so forth. See, whenever data is generated by any sort of equation that has even the least bit of nonlinearity, generally but most of the time data, when the forces that produce data end up producing clustered data. So let me illustrate this with a very obvious example. You lie down in your backyard, because that's, I guess, in these days, that's all you can do at night. Go to your backyard and in your patio, just lay down and look up. If you're lucky enough to see stars, or if you remember seeing stars, what do you notice? Are the stars uniformly spread in the sky, or are they clustered?
Mostly clustered.
In fact, those clusters are what we call the galaxies and the constellations and so forth. So that is a very important point. The sky would be very boring if it was just a uniform distribution of stars. But interestingly, all stars belong to clusters that we call galaxies. Our galaxy has a particular shape, another cluster has a different shape, another galaxy is very different looking. We belong to a spiral galaxy. There are other galaxies which look different, more globular and things like that. So they come across in shape. If you just stand, if you look obviously at any city, you'll find clustering by design. You know, residential houses are clustered, the commercial houses are clustered, and so on and so forth. But go back 100 years and you see people, when they settle down on a land, on a new piece of land, it is human tendency to form clusters, their little communities, their little villages and so forth in the towns. Clusters, cities are quite literally clusters on the map, of population clusters on the map. It's everywhere. If you look at the way the mail comes, whether it is email or it is physical mail into your mailbox, you would agree that mails come to us from of fairly independent agents across the world. Right? Some marketer sends you an email, and there's a lot of that. Then spammers send you email, and your friends may have a reason to occasionally send you emails, and then your colleagues send you emails, family sends you emails. But if you look at the number of emails that you receive in unit time, let's say a day or 6 hour or hourly or something, depending on the intensity of things you do, you'll observe a very interesting phenomenon. You'll observe that mail comes in bunches. Even though these are independent agents sending you emails, some days you will get a lot of emails, or it could be Twitter messages or whatever it is. You'll get a lot of them. Another day or another unit of time, you may feel that not many people are remembering you or sending you emails. You look at your mailbox, one day your mailman will suddenly deposit a lot of physical mails. Another day you might not get any mail at all, or you may get a very, very small number of mails. Oh, why is that so? Ultimately, these mails are all coming from independent agents. Uh, one would intuitively think that every day you should get a more or less uniform bunch of emails, and yet it is not. Mails come in bunches. You stand on a highway, on an overpass of a highway, and let us say that you don't have a congestion on the road. Traffic is on the highway is free flowing. If it is free flowing, one would say that cars should be uniformly distributed across the lanes and equally separated in any lane. But actually, it's not. If you ever stand on the overpass and look at traffic, free flowing traffic, you notice that cars come in waves. They come in bunches. They come in clusters all the time. In fact, wherever you look around you, you'll see clustering in nature, in physical data, in biological data, chemical data, financial data. Everywhere you see clustering. So clustering is pretty much a given, and most of the time it is there, unless there is a deliberate reason why clusters should not be there. So for example, if you take a complete still bottle of water, one can argue that inside it the molecules are not clustered, are not very noticeably clustered. They are fairly uniformly spread in the liquid. Or in a gas at steady state, all the molecules are essentially not clustered. They are all uniformly bouncing around. Right? So there are situations where clusters are not there in data, but quite often they are there in data. But the same, for example, gas molecules, if you look at, and you plot the kinetic energies across, if you look at the space of kinetic energies, so forth, you'll again suddenly start seeing that they are clustered around certain values. Right? So it depends upon how you look at the data. One way or the other, you'll end up noticing some or the other form of clustering in the data. In fact, absence of clustering is one of the things that should always surprise you. It's fairly hard to detect a situation where there is no clustering. So for example, when people would tune their radio the old-fashioned way, uh, if you are not tuned into a station, you would hear what is called static or white noise. You guys have that experience? I don't know if anybody still uses a radio, but if you use the car radio and you tune into a channel that doesn't have a station associated with it, a frequency that has no station associated with it, broadcasting, you seem to hear static. And for the longest time, people thought that that is white noise, that is absolutely uniform noise. There are no frequencies special. Till they discovered that actually it's not. What we are hearing in that static is a very subtle signal, a very subtle pattern. In fact, we are directly hearing the proof of the Big Bang. So when the universe was created, the Big Bang that happened, the reverberations of the Big Bang as a microwave, as microwaves is still there, and we are seeing the microwave background signature of the Big Bang. So quite literally, you are listening to the reverberation. So in some sense, the aftermath of the Big Bang, and it's very clear in front of you the proof that we had a big bang that created the universe. It's very interesting. So finding situations where there is no clustering is hard. In one TV show, which was Numbers, the first episode was that there was a crime situation in which the criminal was committing crimes with no pattern, like locations had no pattern to it. It was not localized in one place or the other, and so on and so forth. And one of the things that the way they solved the crime, when the mathematician genius was there, and he solved the crime by saying, you know what, there has to be a pattern, number one, and secondly, the fact that he is doing it like this means he's trying to create a situation of no patterns, the CL killer. And he used that information to dig deeper and then posited that there is actually an underlying pattern. Discovered the pattern and then discovered the error and so forth. So patterns, that's the value of patterns and clusters. So with that sort of a background, let us now launch into understanding how would you find clusters. So we all, I hope, agree that clusters are everywhere. With some rare exceptions, data comes clusters. So clusters are algorithms.
Sir, one question is that always a given that data always come in clusters? What if on the case of
You should use the word almost always comes clustered. Like an example, if you're looking at the location of molecules in a gas, in a steady state gas, then there won't be clusters. Or a location of molecules in a
Hello, are you guys hearing Asif's voice?
No.
Okay, so it's not on my end. I just want to confirm. I keep losing his voice. No audio, Asif. Hello. Hello, Asif.
I think he has dropped out. Hurry and join back.
He seems to be on. Hello, Asif.
Everyone. I just called him. He says there's some power issue going on, and he'll be back soon.
Okay, thanks, Dennis.
It looks like Omkar is the host now.
Oh, yeah. By the way, we have compiled some quiz questions and posted them on Slack. If you guys have time, just thanks.
I think the attendance is lower today, right, Pachi?
Sorry, Hari. What?
The attendance is much lower today, I see.
Yeah, I think we have what? 18 people?
So, Asif, what would be the percentage, the question that you had asked earlier? What would be
Right.
the percentage
I,
of clustering?
it would be close to 99.5%. Most of the time, we have clustering in data. In fact, if you don't see it in one way, if you change the situation, look at different parameters of the phenomena, you'll see clustering. Like, for example, if you look at the kinetic energy of the molecules, then suddenly you'll start seeing different clusters, one cluster for oxygen, one for nitrogen, and so on and so forth, in the same uniform gas. So clustering is there one way or the other. It depends on what you're looking at. So rarely data presents itself without clustering. So um, generally your assumption should be there is clustering. Now it's a question of how poor or how rich the clustering is. Absence of clustering is very, very poor clustering. It's another way to put it. You should assume there is clustering, and we'll learn the techniques, how to know the quality of the clustering. That is a topic for today. So now comes clustering and detecting clusters. So let's go back and take this example again. Suppose I have data points like this. And you have data points like this. In how many ways can you detect clusters? So the first method that you can think of, and we'll do three kinds of methods. One is k-means clustering and its relatives. So k-means is the original clustering method, very simple, the most often used method. because of its sheer simplicity. It is to clustering what linear regression or logistic regression are to predictive modeling. Then we will learn about hierarchical methods, or agglomerative clustering, clustering, and we will also learn about a third class of clustering methods called density-based clustering.
Asif,
Yes,
I'm sorry. Has the recording been started?
yes, it has been.
Okay.
Let me verify that. Yeah.
Start the recording.
So we will learn about 3 different types of clustering. We might not learn about all of them today, but we'll learn about them. So k-means clustering. K-means clustering actually solves half the problem. If you ask, you cannot ask how many clusters are there in the data. K-means clustering will say, I don't know, you tell me how many clusters are there, and then I will go and find it. And if you're wrong about the number of clusters that you expect to see in the data, it will essentially nonetheless partition the data into as many clusters as you want. So here, for example, you notice that a good partitioning would be 2 clusters, isn't it? So you give k is equal to 2, it will find the 2 clusters very nicely. But if you give k is equal to 3, then it will start somehow forcing the data into 3 different buckets or 3 different clusters. And you don't get a good quality clusters. Right? So a k-means clustering has the limitation. You must specify k, the number of clusters, the number of clusters to detect. Now, it turns out that it's not as bad as it looks, because there are techniques that we can use to, even with k-means clustering, by doing it again and again and seeing which value of k gives us good clusters, we can actually guess what is a good number of clusters to see in the data. But for now, we will just say, this is our situation. So how do you solve it? K-means clustering actually starts with these assumptions. It says, pick, in the simplest form, pick k initial points as cluster centers. Cluster centers or centroids. The word is centroid. And you'll see this word centroid used in the literature. So let me also use the word centroid as cluster centroids. And then B, assign all points to their nearest centroid. This is it. And the C part that comes up is quite interesting. Find the center of gravity. Find the new centroids in each cluster. But before I go there, let's understand what is a centroid. So suppose you have a bunch of points here, and you ask, what is a centroid? What is a centroid here? Centroid is the center of gravity, you can say, or center of mass. Right? So, for example, if all of these points, you think of them as marbles, right? Where is and they all weigh something, then you intuitively realize that there is a center location, a point, or it may or may not be a point, but it's somewhere there, right in the dead center, which is the center of gravity. So that if you were to put your finger there and hold all these points up, it would stay at equilibrium, sort of like that. If you think of all of these points as on a sheet of paper, or the marbles on a sheet of paper. So is the centroid is the center of gravity. Centroid, let me write it down. Centroid is the center of mass, rather, if you think of each point as having some mass, point xi as having a finite uniform mass, uniform mass, right? So that's the meaning of this centroid. So now that we have set the stage, let's do it. And the last stage is repeat. D is repeat. Repeat B and C over and over again. That's the algorithm. So it is very intuitive when I explain it to you, and you'll see that. So let me start with some points. Right. So suppose I randomly pick 2 points. Which 2 points would you like to pick? Suppose, if you're lucky, we'll end up picking a point. 1 point will belong to one cluster. Let's say that if you're lucky, we might end up with a situation like one random point we might pick up as this, and another random point we pick up as this, right? They belong to 2 different clusters. But let us say that it is not the case. So let me go back and say that actually you ended up picking accidentally 2 points that are actually fairly bad. Let's say that you ended up picking these, which 2 points? These 2 points. I'll just circle them. Suppose these are your initial guesses. Right? Let me just mark them as the initial guesses of centroid C0. These are your initial centroids. And now what you do is you assign to each point the nearest centroid. So you ask yourself, which of these centroids should it belong to? So if you look at these points, this point is closer to C1, this is C. So if I were to draw a decision boundary for C2, it would be not a decision boundary, a clustering boundary. I would say that this is the space for C2, and this is the space for, let me mark this, C1. Is this a good belonging, like assigning each point to the nearest centroid? Would this be a good separation, guys? Do you all agree? Is it obvious what I did? Anyone?
Yes, sir.
It's pretty obvious, right? So this is a step number 1. Step 1 is pick. Step number 1, just pick some centroid. Step 2 is you assign it. Now we come to step 3, the crucial step 3, which says that for each of the clusters, find the new centroid. So let me use a different color now. Yeah, let me pick a different color. What is the centroid of the C1 cluster? Would you agree that the centroid is probably this guy? Right? So this is C1. Let me use the word C0 and this C1. Would you agree with that? And if you look at this, perhaps the centroid is something like, would you say this is the person approximately? C1, 2. In the second iteration, in the first iteration here, this is the centroid of the cluster here. Would you agree, guys?
Yes.
The second cluster, this is it. And now you play this game again. This time when you play this game, you'll realize that all of these points belong to C1 prime, and all of these points belong to C2 prime. So that's beginning to look pretty good. Now let's do this game. And so the whole idea is that was step 2. Now repeat this process. What is the centroid of all of this? Well, the centroid of all of C1 prime cluster, green cluster, is pretty much, I guess, not likely to move much. It will remain more or less the same. But for C2, so let me just say that this is still the same. This one probably will become this, right? Let me call it C prime prime 2, and this is also C prime prime 1, right? And now you realize that your cluster now, what is the journey of the cluster? If you look at the journey of the cluster, this, give me a moment, guys. So journey of the cluster is this cluster, it started from here, it went to this, and from this, it hopped to this and pretty much stopped. C1 didn't migrate much. It went here and it sort of stayed here, right? But then what happens is after a few iterations, here about 3, you notice that the centroids are not moving much, and the other observation that you have is at points, data points are not migrating from one cluster to another. Do you notice that? It's a very simple observation that we just went through 2-3 iterations, and then we noticed that we have actually found the center and the clusters. And once you have done that, you say, okay, we are going to stop. So in this particular case, the stopping point would be the 3rd iteration. And so you would say the blue cluster is it. This cluster, right, is it. And this point is your main point. And this point is where you stop. And this is your cluster, right? And thus you have discovered clusters. Are we together, guys? Was
Yes.
that easy? Yeah. I hope that was easy. That was straightforward. So this algorithm is very important. It's k-means clustering. And it is surprising that we can find clusters with such a simple algorithm, especially in view of a different result, which is that you ask yourself this question. When we take computer science, we sort data. You know, we search for things in data, we sort data. And we learn the big O notation that says, okay, you can do sorting and searching in order, and order n square for bubble sort, order n log n for quick sort, and sometimes linear search, order n, and so forth. It's all impressive, but you always find a fully sorted order of elements. So people wonder that can we not find clusters in a very straightforward way? Why is it an exercise in machine learning? And then comes the result, which says that actually finding clusters in an absolute way, deterministically, is a nearly impossible problem. In fact, it is considered to be at least NP hard. Now, when a problem is NP hard, means it can only be solved in non-polynomial times. At least it is that hard. It's a computer science or algorithmic like a sort of language, right? So in that language, you say it's a very, very hard problem to solve. And there is a reason for it, because what you call clusters, it depends upon how you look at the data. So I will illustrate this with a point. Suppose you have data here. And then you have another cluster here. Let's say another cluster here. And another cluster here. And to add to the noise, let me add a situation like this. Now imagine that obviously there's some outlier points here and there. So the question is, how many clusters do you see? If you look at this data, how many clusters do you see? Well, it's hard to say. You can argue that the entire thing is one cluster. Right? So this is your k is equal to 1. There is just one cluster. You can alternatively argue that there are actually two clusters. They are this and, sorry. They are this and this. Do you see that k is equal to 2? You can continue to argue that no, actually, there are not two clusters. You see actually 5 clusters, right? 1, 2, 2, 3, 4, 5, right? Do you see this, guys? K is equal to 5. Are we together? So there is an interpretational aspect and the resolution aspect. At what resolution are you looking at the data? Are you looking at it macroscopically? Are you looking at it microscopically? And then you can go even further if you so choose. You can go and argue that within clusters are clusters. So this is one cluster or within the cluster, right? And things like that, a subcluster. Why is this so? A subcluster cluster. So therefore, because there is further clustering inside a cluster, it is not determinate. It is hard to fix a number. Do you see that? And that is what makes this problem computationally NP hard. You can't do it. You have to use probabilistic methods. In other words, machine learning methods. K-means is like that. It will randomly start with 2 points and it will do clustering. And if you start from different points, you might occasionally end up with completely different shape of clusters. It's the nature of the beast. Right? So that is something to know, that clustering is a machine learning. It's very non-intuitive. See, the human eye looks at a beach and immediately spots the clusters of people. It looks up into the sky and immediately spots the galaxies. The human eye is a marvelous computation machine. It instantly detects clusters. We look at data and we don't have to be told. We just look at it, and even without education, without any training, we can tell, oh, we are looking at clusters, right? This must have been evolutionary, even when our great ancestors were fishes in the sea. You know that fishes roam around in schools, clusters, right? We would notice a cluster of fishes, a school of fishes, one species of fish, another species, and a big whale cluster, and so forth, a family of whales going by. So cluster is something we learn to detect in our neural systems a whole long time ago. But for machines, in fact, for the human optical system, the estimate is that it has gone through close to at least 100 million years of training. I think it's 100 million, not 100 billion. Yeah, 100 million years of training of the, if you think of it as a machine learning algorithm, it has gone through 100 million years of training and evolution. On the other hand, when we try to train machines and we try to do clustering, obviously we are dealing with much more primitive things. Right? We don't have that level of sophistication in our AI machines. I'm just putting it in perspective because these days it's very fashionable to say that the singularity is near and the robots are going to take over, or AI is going to take over. AI is at least 100 years from doing anything whatsoever intelligent. The, the joke is that AI doesn't need to really be intelligent. Even as dumb machines, they are taking over, which is a different thing. So that is k-means clustering. Now, one question that arises, how do I know, given the fact that k is not specified, how would I know what is a good k? So what is the metric? Just like in regression, we had the R squared and all of those measures, mean squared error. What is the, and classifier, we had the confusion matrix. What is the metric in clustering? And there are many metrics, but one metric is that once you create the clusters, what is the within cluster sum squared distance? Very interesting. So what is the within cluster sum squared distance? Let us say that these 5 points are a cluster. Let us say that these points form a cluster. Then what you do is you take any arbitrary point xi and every other point xj, and you find the distance between them, distance xi, xj, right? And square the distance, and you find the sum of all the ij belonging to the cluster. Let me call this cluster C1 or just C. So this is very interesting. You have to find every pairwise distance. Right? In other words, every possible link you have to compute. And I don't know, did I miss something? This looks like a fairly complete graph. So you have to find all the pairwise distances and square them all. And when you square them, then you divide it by, there's a normalizing metric, right? People often put a normalizing metric, how many points there are and so forth. So this is called WSS. Within cluster sum squared distance. Let me write it. So for this cluster 1, let me just call it C1. Within cluster sum squared distances. Okay? So now what happens is, suppose you have detected three clusters in data, C1, C2, C3. What you will do is, for your entire clustering algorithm, you compute the overall or total by saying WSS1 plus WSS2 plus WSS3, right? Or more formally, suppose the number of clusters is whatever it is, K, you would write it as a summation over K of WSSK of the kth cluster. And obviously, you add them up. And if you substitute the original value, you would come to the conclusion that this is summed over K, summed over Ij within a cluster belonging to a cluster, right? K, and a D squared xi, xj, right? Any 2 points, and then over each of these are appropriately normalized, and you can give the normalization scores, total number of points and so forth. So this is your, I might be a little bit off in my expression, but this is the intuition behind the WSS. What can you do with this WSS? What you can do actually is, you don't know what K is. So you build something that is famously called the Scree Plot. Scree Plot. You take different values of K. K is equal to 1, K is equal to 2, 3, 4, 5, and so forth. And what you do is, for each of them, you compute the WSS total. You compute the WSS total. So what you will notice is that, let's say that WSS for the first one is this. For the second one, it will be like this. Right? So then for the third one, it will keep going down. WSS will keep going down. Then this. So if you connect these dots, you will get a curve that looks like this. This is called the Scree plot. And what you look for is an elbow. Can you guys detect an elbow? At what value of K do you see an elbow in this curve? A bend in the
About
curve.
K minus 2,
5, 1.5.
K equal 2.
Is equals to 2.
Close to 2.
K is equal to 2. And so in this data point, you would say that the optimal number of clusters is equal to 2. Right? K is equal to 2. This would be your optimal number of clusters for this data. So that's how your WSS will keep on decreasing towards 0 as you find more and more cluster. In the asymptotic limit, where you take, let's say that number of clusters is the same as number of points. Well, each point is a cluster, so it is not far away from itself. WSS will be 0. So this keeps decreasing, but you don't look for the minima, you look for where it is a bend. Or more practically speaking, you look for the point of diminishing returns. At what point the returns or the decrease in WSS is not much afterwards. And that point is around K is equal to 2. Yeah? So this is called the elbow method. It is often called the elbow method of finding cluster count. Right? So that's what it would be. Now, so that is all there is to k-means clustering. You can determine k-means. So now what it means is it's problematic. You need to keep running k-means clustering again and again with different values of k till you latch upon the best value of k. So now I'll go back to the old question. What if there are no clear clusters in the data? So here the elbow is clear when the clusters are not well formed or they are not globular. And I'll explain what it is. They are not globular. Then Scree plot does not show a clear elbow. What does that mean? Right. So let me explain that. It's very intuitive actually. So suppose you know that you can keep trying different values of k. What will happen to WSS is that it will just show. So can you guys detect an elbow in this curve?
No.
No, sir.
Not very clear.
Yeah, it's very clear. So very poor clustering, very poor. So causes, very poor clustering. That could be one cause, or not. Think of it as roundish, right? Nice round convex surface is globular, right? Like a globule. So when it is not, for example, if your cluster looks like this, right? Non-globular or non-convex. In such situations or in such a situation, what will happen is that k-means fails. K-means does poorly. poorly as an algorithm. So this is it. And the third thing is that if you get a situation that is like this, more or less a straight line, right, may indicate you more or less homogeneous data without clusters. So you see that clustering is so weak that it's more or less homogeneous data, or non-globular clusters, very strange shaped clusters. Are we together, guys? So it is not. And so this question was raised, what if there are no clusters? One clear indication from data is something like this. And I have seen in practical terms, guys, I lead a fairly large, in my day job, I am the VP of a R&D group, in the true sense, research group. So we do a lot of analysis of data, and it does occasionally happen that a data scientist will come and say that, you know, I cannot clearly see how many number of clusters to do using k-means clustering, and what do we do? And the general idea is that you ask yourself, are there clusters in data, or is k-means the best means to find it? Your next course of action usually is, don't use k-means. It is probably not a good algorithm. Go try other algorithms. If all algorithms say that there are no good clusters, then probably data is uniform. And of course, by taking samples of the data, you can quickly check if there is a homogeneity in the data. So it is an exercise worth doing. It keeps coming up all the time. So, and the reason I mentioned it is that most textbooks, they overemphasize k-means. K-means is very simple to understand. And one can understand why people just talk of k-means. And then they talk of hierarchical clustering a little bit. And actually, most of the modern methods of clustering that one should use are almost never mentioned in textbook. It's a very peculiar situation. What you would actually use in data sets, the sort of algorithms, quite often are not discussed in the data. K-means works, but it works only with roundish clusters and clear, very well-defined clusters. There are situations where clusters are well-defined, but there are also large class of situations where actually clusters are very peculiarly shaped, and you need different algorithms to find the clusters. So let's go ahead.
Would you mind giving some examples where k-means, like some practical examples where k-means clustering is helpful and where you see this clustering?
We will literally do that example in our labs. Okay. So next time, right, we will really deal with that. So for example, if you look, for example, galaxy data, stars data, generally k-means works for discovering a galaxy more or less like our galaxy. A spiral, but you can still shrink wrap it in a hull, in a sort of a globular shrink wrap. But there are galaxies whose shapes are very linear, pencil thin, and that don't show the kind of structure, the globularity that you hope for, then it doesn't work. And for example, when you look at intergalactic cloud and so forth, look at the very beautiful picture. In the cover of the notes that I've given you are the pillars of creation. I don't know if you guys know about that. Yeah. So one of the most interesting things is I give the data and I ask people, usually when I am interviewing people who have PhDs, and you have to see whether they are able to think. You're not hiring them for just writing a ton of code, or being able to code. You're hiring them for their ability to think and reason through. So sometimes I give that data and say, okay, how would you find clusters in this data? If you look at the data, it's very interesting. It sort of has clusters, the two pillars of creation, the big pillars. There are. But if you were to try traditional clustering algorithms, they actually don't have complete success. They have certain degrees of success. And That's an example where these things don't work. And by the way, the history, and let me take that as a point to go into the bit. Those pillars of creation are my favorite for a historical reason. If you're in astronomy, you probably know that. Anybody who has done astronomy, one of the great milestones in astronomy was the Hubble telescope. Some of you may have heard of the Hubble telescope. In my generation, it was a very big thing. When the Hubble telescope was launched, it was this giant, massive telescope that was put out in orbit, in the Earth's orbit. So free from the atmosphere, it did not have any of the noise factors. And so it could look into deep space very, very clearly, right, without disturbance. And one of the first things they wanted to see is this picture, which astrophysicists and astrophotographers love, the pillars of creation. And the picture itself was so startling, so rich, that a lot of people believed that the entire investment in the Hubble telescope essentially paid for itself on the first day, right? In the data that it gathered in the first day. Astronomy as a subject would never be the same. Right? With the Hubble, we discovered the microwave background, we discovered many, many things. Just one telescope led to countless discoveries. And the picture that you see on the cover of it was the last picture the Hubble took. So when the Hubble was being retired, one thing that they did is they decided, let's go back and look at where it looked as the first picture, the pillars of creation. And it looked at that, and the picture that you have on the cover is the high resolution picture. One is in the visible spectrum, the other one is in the X-ray spectrum. Two different spectrums. So you see two different sort of data coming out of it. And it's very interesting. Play with this sort of data and you'll see. So not always are clusters globular. Our intuition thinks of clusters as globular, roundish shape, but in practice it may not be so. All right, guys. So with those words, let's take a quick break. It is 8:30. Is it 8:30? It is 8:33. Let's get a 20 minutes break. So 33, 43, 53. 53. Okay, let's meet at 5 before 9. 5 minutes before 9, guys. Would that be reasonable?
Asif, could you please scroll up to the within cluster sum of squared error calculation? Just want to.
By the way, let me check the exact formula. I've given you the intuition and the exact formula. This dividing by 1 by n. I might have made a mistake. Let me check that.
Within cluster sum squared distances.
So the idea is for each cluster, you find this WSS for each of the clusters. And once you have found the WSS for each of the clusters, now you go and add up all the WSS.
So what I don't understand is this distance you find with the centroid that you have chosen to the point of any points in the cluster, or to any from any point to any point.
Pairwise point. It is not from the centroid to each point. It is every pairwise point.
Okay. So that distance must be minimum to.
So that what you do is that gives you a loss function or something to minimize. And you try to find the cluster, that clustering which minimizes that loss function. So WSS is the loss function. It's a traditional loss function for clustering. There are other things that you can formulate, but this is it.
Within a cluster, okay.
All right, guys, let's take a quick break and let's gather right after that. 5 minutes to 20 minutes later, 5 minutes to 9. I'll pause the recording for now. So just to review k-means clustering. K-mean algorithm has a basic premise. Start with a few data points, call them the real centroids or the initial centroids, not real centroids. But then go through a cycle. The cycle includes 2 steps. Assign each data point to the nearest centroid, and then then you have new centroids, you have new clusters. Once you have the clusters, once you have assigned all the points to at least one, to one of the centroids, to the respective centroids, recompute the centroid. And Once you have recomputed the centroid, repeat the cycle of assigning points to centroids and recomputing the centroids. And as you iterate through this process, you'll converge. You'll converge to a stable solution where you'll notice that centroids are not moving, right? Are not moving much, and the data points are not changing loyalties between centroids. They're not migrating from one centroid to another. When you reach that point, you know that you should stop. Now, the other point I mentioned is that why is it so hard to find clusters in a deterministic way? Partly because how many clusters you look for in a data is not clear. It itself is a judgment call. For example, I took this example. Do you see one cluster, two clusters, 5 clusters, or how do you see? There are clusters within clusters. So it's a hard problem. We talked about WSS being the metric within cluster sum squared distances. These are the pairwise distances between any 2 points in a cluster. We talked about the Scree plot. Scree plot, make the Scree plot and you look for the elbow, which is why colloquially it's called the elbow method. And then we talked about the fact that in the Scree plot should give you some insight. Do you have well-defined globular clusters or not? If you find no elbow, then maybe there are no well-defined globular clusters, which means that either there are no clusters or that they are not globular or roundish in shape. And in the extreme case, when the clusters are completely missing, then it is like a straight line. You don't see it's just uniformly coming down. WSS will come down. So this is a k-means clustering. It raises the question.
How will you do the outliers here? How will you approach the outliers in this for the k-means?
Actually, it doesn't deal with outliers. That is its limitation. It insists that every point belongs to a cluster.
Okay.
If there's an outlier, it will say, no, you belong to this cluster. Or if you were to take the example of somebody living far off between 2 cities, which are really, really far off. Let's take an example. I'm told that if you're traveling through Wyoming, the distances between cities can be as much as 50, 60 miles or 100 miles. In such a situation, actually, somebody once told me that if you are coming with a truck, a big, one of those 18-wheelers or 16-wheelers, you're thundering down one of the interstates. Somewhere near Wyoming, you will see, or somewhere around there, you will see a billboard for a restaurant and a nice recreational stop, which is far away in either the state of Washington or Oregon, I forget which. So you can imagine how barren those lands. So suppose you are in one of those places and very far from both the cities that you left and the city that you're going to. You would argue that a little hut or a little cottage in the woods really belongs to none of the 2 cities. It's a stretch to call it to belong to the cities. K-means clustering, on the other hand, will insist that it belongs to one of the cities, which is its weakness. Okay. Take another clustering algorithm. This cluster.
But the only motivation for me to ask that is because if we can identify that, then the number of repetitions that we have to go through to come to the correct k would be drastically reduced. That's why I was asking that.
Good point. It's a good point. Actually, people do that. So see, the k-means, the basic k-means has many improvements that people do. One of the improvements is they won't take randomly, let's say 2 points, we are doing k is equal to 2. They won't take any random 2 points from the data. They will take a random point and then they will find a point which is furthest from that data point, as far away from it as possible. And they will take that as a second point. And generally that converges faster, because if you were to think about it, if you go back and look at this cluster, if I take a point here, if I take a point here, this point, and the furthest from this point would be this point, right? Yeah. And so
it's not visible, sir.
Oh, my screen is not visible?
Screen is visible, but cursor is not visible. Like
Cursor is not visible. Let me make this. Suppose I take this as one point. The point furthest from it would be this point, the one that I marked red.
Yeah.
Isn't it? And so you can imagine that clustering will be very, very fast, right? In 1 or 2 cycles, it will converge. Isn't it?
Okay.
It's already near the correct answer, basically. So all that will happen is this will move maybe one step here, and this will move one step here.
Okay.
And you'll be done in one cycle. So that is one. The other thing people do is they look at the distance of point from the center of the cluster, the cluster. After one cycle, they may look at some optimizations. And they may actually not count points that look like outliers and so forth. So, you know, K-means clustering has a wide body of adaptations and improvements, and there's a vast literature.
Okay.
So one of the things is, you know, we are assigning point by point to each centroid, which is very, very inefficient.
Right.
One thing people can do is, can you assign entire regions to it? So for example, if you look at this point and this point, you can essentially say that this entire region belongs to this point, the red point, isn't it? So assign entire regions. And to do that, there is a very lovely bit of a specialization of k-means. They look at some data structures called KD tree, k-dimensional trees. They break up the feature space into a tree-like partitioning. And in a partition, there'll be many, many points, and they assign an entire subregion to one of the two centroids. It happens very fast. KD tree was one of the first acceleration of k-means clustering. Otherwise, it's a bit slow. And then people did a lot of other work. KD, instead of KD tree structure, they started using cover balls and so on and so forth. And then there are so many adaptations for it that people started creating metric trees, the whole class of such things in which you divide the space into regions.
Okay. Yeah. Thank you.
Lot of very interesting body of work. But see, today is an introductory class on clustering. So we are just sticking to the big highlights. We are not going into specific. I mean, there's a lot. As you read it, you'll be, you know, let me put it this way. There are people whose entire life is to research clustering methods. So think about that. There are many, many PhDs. And if you really want a PhD in a hurry, you can write one more clustering algorithm, show that it solves some sort of problems that other clustering algorithms cannot. And well, you have a winner.
Okay.
Yeah. It's a very fertile field, actually. So the other form of clustering is called hierarchical clustering. It is in your book, so I'll mention it. Let me just say hierarchical or agglomerative. Clustering. Agglomerative clustering means it's a bottom-up approach. It is also typically called hierarchical clustering. It is actually computationally very brutal. What it says is that when you're given points, lot of points, what you do is you create every pairwise distance. So create this distance, xi, xj, right? And you create a whole list of these distances. Then what you do is you sort it in increasing order of pairwise distances. So what happens is 2 points, which you first find those 2 points in the data set, which are just closest to each other. Are we together? And now here's the rule that you set. In the beginning, declare each point of data to be its own cluster. So suppose there are n data points. How many clusters are there? So number of clusters initially is equal to number of data points, because each point is a cluster. Then what do? You create this list for all the time you maintain a list of distances. And in the list, find the beginning. Once you have sorted it by distances, pairwise distances, find the 2 points which are closest to each other. And what you do is you go and you merge them. You say that these 2 points, let me just call it 1 and 2, you merge them, and your merge point you call a cluster now. So because you create your first basic cluster, let me call it C1, 2, by merging points 1 and 2. Are we together? Then what you do is once you have done that, now there is a problem. 1 and 2 in the list that you have, dxi, xj, this list will contain things like dx1 and something or the other, and dx2 and something or the other. All of these things deleted from the list. And the only thing that you do is compute the distance between d C112, the cluster, and every point. Every point. So you treat this cluster as a point somehow, right? You say that you have merged the 2 points or agglomerated it into a cluster. Likewise, you keep doing and you build a data structure. Sometimes 3 points will be equidistant, you'll merge them. And then you keep on doing this. And then what you do is you end up creating less granular clusters. And those clusters, again, you merge them and you merge them. And then you have, let's say, 3 points here. And you merge them. And then what happens is that you may merge these 2. And then these may be far off and you may merge these 2. So you keep on merging these clusters together, right? You end up with a structure. This is called the dendrogram. This is a well celebrated visualization in machine learning, pattern recognition. In many areas, you'll see dendrograms come in. In agglomerative clustering, this is sort of a picture. If you think back and look at New York Times, or you look at any of those data visualization places, which are textbooks, you'll always recognize somewhere or the other a picture like this. It's a dendrogram. This dendrogram is obviously what it says is that we are merging points into clusters and clusters into bigger clusters, and so forth. So suppose you want to have k is equal to 1, let us say. If you cut here, how many clusters do you see? K is equal to 1. If you want 2 clusters, you can cut here. You'll get k is equal to 2, right? So this cluster and this cluster, this cluster and this cluster will be k is equal to 2, isn't it? If you want to have k is equal to 3, then you just keep changing your cut points. Sorry, this is k is equal to 1 will give you 2 clusters. Sorry, 2 clusters. This cluster and this cluster is k is equal to 1. Sorry, this is k is equal to 2. K is equal to 1 is here at the very top. This is k is equal to 3.
And then we
because there are 3 lines cutting this horizontal line. So 3, and likewise, you can keep on increasing. And what you notice is that the question of what is the best k, what is k, you can solve it in a very visual way, right? You can look at it and see what number of clusters do you make sense visually. And it also answers the question that sometimes there are no perfect answers. So especially in biological domains, sometimes you say, can you bisect the data, partition the data into 2 clusters? And then another person will say on the same data, he'll say, for me, it will be more useful if you cluster the data into 5 clusters. Right? So when you have built a dendrogram like that, it is very easy. You don't have to recompute. It has basically built all the way to k is equal to n. It has done every possible clustering that you can imagine. Are we together? So this algorithm is computationally intensive. it is not a big deal for modern computing systems. So for example, if you have a fairly powerful computer at home, this can be done very rapidly. These days, it's not considered a big deal unless you have gazillions of points. So then it does become computationally brutal. In the days when the computers were not so powerful and people really needed the dendrogram in many fields, it was considered rather intensive computation. Now it's not a big deal. So long as your data sizes are reasonable, but still more computationally intensive than your k-means. So that is dendrogram. But it leaves one question unanswered. One question remains unanswered, to be answered. Which is, what question is that? When you merge a cluster, let us say that I take these 3 points, and here is a point xi. When I merge this cluster, let us say, at some point I merge this cluster, it becomes this. What is the distance of point xi to this cluster? So the distance can be many distances. We can define distance to be the distance between the shortest distance between xi and a point in the cluster. It could be defined as the largest distance between xi and this cluster. It could be defined as the distance from this to the centroid distance, isn't it? But do you see, guys, that we can define the distance of a point from another cluster in multiple ways, isn't it? And likewise, the same thing can be generalized. Suppose I have 2 clusters like this, and I have 2 clusters that I am merging. I need to find the distance between clusters to do this agglomerative process. So what is the distance? Once again, the same reasoning applies. Is the distance the shortest distance? Is it the largest distance? Right? The largest distance could be possibly maybe, sorry, let me not use this color. Different color. Let me use this distance maybe. Is it this distance? Or is it a distance from the center? Okay, actually, I should have used green because in the other picture I used green. So let me say, is it this distance? Or is it the distance from the centroid to centroid? Right. So each of these definitions you can argue is good or bad based on your situation. And so people in the industry, they use a word for it. These are called linkages. The definition of distance between 2 clusters is called linkage. If you look into the chapter 10 of your book, it will talk about the different linkages, right? So linkage or the distance definitions could be shortest distance, shortest pairwise distance, largest pairwise distance. Then it could be also average pairwise distance. It could be distance between the centroids. And so forth, more and more, and other ways. So generally, choice of, depending on the data, the choice of linkage function or the definition of distance does affect your clustering. And generally, you don't know which one is good You build a dendrogram, you look at it and say, for my situation, this looks better. So that is how you deal with the linkage functions. And sometimes it is people make it a hyperparameter of the model. They look at the, pick a linkage function, they're looking for 10 clusters, let us say, and then they will find the WSS or some metric, and they'll try to optimize it and see which linkage gives you better, or they'll visually inspect it, bring in the domain experts and say, which one do you like better? Which one makes more sense to you? And they can answer that. So this is agglomerative clustering or hierarchical clustering. So k-means and agglomerative clustering are the classic, I would say, the clustering methods. They have been there for a very long time. They certainly are there in all the textbooks. All the textbooks have k-means clustering. Some a fairly good proportion of them have hierarchical clustering, but not all of them. And therefore, these are the two classic methods. So before I proceed, are there any questions? Is this clear, guys? Huh? By the way, chapter 10 of your book, go review chapter 10 of your book. Huh? You'll see it there. Go ahead.
Can clustering expose confounding variables in the data?
No, it doesn't do that.
Oh, so you just don't know how the data specifically behaves, but you can separate them distinctly.
That is right. It's a simply pattern recognition, cluster recognition. So it is silent on the question of are they confounding variables.
Can you go over again the how to find out the K looking at the render?
So what you do is you maintain a long list of all pairwise distances between the clusters. In the beginning, each point is a cluster, right? So what you're looking at is the pairwise distance between the points. And so what you do is always at each step, find the shortest pairwise distance and you merge those two clusters into a bigger cluster, right? And you keep on repeating this process. When you keep on repeating this process, the only thing that is unclear is what is the definition of distance between two clusters? That is called the linkage function, right? Or linkage simply. So you can look at the shortest pairwise distance, take a point which is in one cluster, another point in another cluster, which is as close to each other as possible. You can take the furthest pairwise distance. You can take the average pairwise distance between centroids, and go about thinking more ideas you can do. Now, in this, that is hierarchical clustering. Does that make it clear? Yeah. So now one thing is there. There's a mistake that people make. Look at point 1, 2, and 3, 4. Now compare a 2 to 3 and 4. Is 3 closer to 2 or 4 is closer to 2? So for new students, this is a puzzle. Is 3 closer to 2 or 4 closer to 2? Would you make a guess? Anybody make a guess? How would you, looking at this picture, 2 is,
Oh,
go ahead.
I think it's hard to tell because you just see the relationship of 3 to 4, and then they were clustered already.
Yes.
I'm not sure if the dichotomy there shows that they're supposed to be related between 2, 3, and 2 and 4, but you can tell 3 and 4 are close.
So what happens is that when you compare the distance of 2 to 3 and 4, just because 3 in this diagram looks to be closer to 2, doesn't really mean that they are closer. You say that as far as the dendrogram is concerned, 2 is equally separated from 3 and 4. Why is that? You look at how many links later do they meet. Does 3 meet 2 first, or does 4 meet 3 first? 2 first. But actually 3 and 4 get merged into this, and 2 gets merged into this, and they both meet here at the same point. 3, 4, and 2 meet at this level. So you would say their distances are the same. So this is a fallacy to remember in a two-dimensional representation, because it is a two-dimensionally, the dendrogram is, it often gives you the misconception that things that look on the picture close to each other are closer. But the way to look at distances is to look which meets first. So for example, 2, and let us say that this point is 5 and 6. So if you compare the distance of 2 to 3 and 2 to 5, right? So if you look at this, then you would say that 3 is closer to 2. Why is it closer to 2? Because 3 meets 2 right here itself, whereas 5 meets 2 here, way up here, right? At a higher level. So if it meets at a higher level, it is further away from 2. So that is the way to interpret a dendrogram. Are we together, guys? So that's what a dendrogram is, and this process is called hierarchical or the agglomerative clustering. Agglomerative means you coalesce points together, right, and you build it up, a cluster.
So Asif, so you said that this is computationally intensive. Like how much data are we talking about when the computation is not practical to apply anymore? Like when the dendrogram is not practical to apply anymore? Like 100,000 cases, or how big a data are we talking about?
See, it depends on whether you're doing it on your laptop or with 8 gigs of RAM, or whether you're doing it on a powerful workstation, or you're doing it on a cluster of machines, like, a server cluster, big data cluster or something. If you're talking about a big data cluster or something like that, with a distributed computation, you can have 1 billion points and it wouldn't matter. It will finish one day. Right? If you are doing it on the laptop, then even 1 million points will strain it. Even 100,000 points may really stress the laptop. So it depends upon the computational hardware available. These days, we don't consider these classic methods to be very expensive. There are other methods which can get more expensive and so forth. But on the scale of things, you just consider it as business as normal. If you have to do it, you do it. There is another thing that people do. Sometimes they don't want to cluster the whole data. What they will do is they'll take a sample of the data, cluster it, and then assign all the points, the remaining points, to the nearest clusters. Are we together? Right? So that could be an alternative that people do. You just don't, if you have 1 billion points and you must do it on a laptop, take a sample, right, and cluster them. And then suppose you have to find k is equal to 6 clusters. Then so you just cut it at that level 6, find the centroids, and then ask the remaining points which of the clusters or centroids do they belong to, and assign it to that. So people have found clever ways to work around the computational aspects of it. But by and large today, because hardware is so plentifully available, you don't worry about it anymore. But just don't go with 1 billion points on your laptop. It will just bring it to its knees. Or even 1 million points. Don't do it on a laptop. Take a sample and do it. That's what I would say.
Asif, a quick question. So you said the k-means is NP hard. Is the hierarchical NP hard or NP complete?
Hierarchical, actually, no, clustering itself doesn't mean k-mean or not. K-mean is not NP hard. But if you want to see, but remember that machine learning algorithms are probabilistic algorithms, right? There's always an element of chance to it, of the clustering. But if you ask this question, so forget machine learning approaches, both these approaches, forget it. You ask this question, why is there no absolute guaranteed way of clustering that will always find the right number of clusters in data? And the answer to that is nobody has found such an algorithm. And we know that even if such an algorithm is one day found, it is at least an NP hard algorithm. So nobody has ever found that algorithm. And nobody expects that algorithm. Instead, what we do is these methods, the probabilistic or the machine learning methods to find clusters. And it sort of goes to answer the question, we can sort, we can search, why can't we cluster? And the answer is clustering is an entirely different kettle of fish. It needs machine learning to do it, not traditional algorithms.
I see. Because I thought the leaf level you're doing NC2, like you're choosing choose to kind of what do you call n into n minus 1 by 2 kind of a pairs are compared, and then the next level those clusters are then compared against each other and recursively so on and so forth.
Yeah. See, hierarchical question will give you an answer. It's a machine learning method. The problem is, what is it that you're optimizing? At the end of the day, you have a loss function, and you optimize a loss function and you find a inflection point. Sometimes you find good inflection points, sometimes you find an elbow, sometimes the elbows are not visible. What do you do then? So it is not a guaranteed method that guarantees convergence. If you're sorting, convergence is guaranteed. But in clustering, there are no guarantees. None of the algorithms gives you guarantees.
Got it.
That's the point. And that's where machine learning differs, guys. In business, if I may give you a practical example, it is common for some businessman to do a startup and hire a bunch of data scientists and give a problem that they say you must solve it. And usually that's an odd approach, because the right approach is to take the data, let the data scientists find something in it. Once they have found something on it, then to build a business around it. But when you already have a business problem and you hire data scientists to solve it, it may or may not be solvable. No, the quality of the solution may be quite variable. And then people have, and I've heard it, they say that, I thought I hired a stellar data science team. They all have very good pedigrees, but they're absolutely useless. They don't seem to be producing results. And many companies, you hear this thing, oh, data science team is, we are unimpressed with the results they produce. Usually, if you look at it, it may be that they hired these days anybody who can draw a line through 2 points calls himself a data scientist. So if you leave, so there's a lot of fakers or very rudimentary data scientists. But if you filter them out, if you look at good quality data scientists, still there are no guarantees to success of a project, because ultimately data is king. So for example, if I ask you, can you tell whether somebody has diabetes or not? Based on the color of his shoe and the color of his pant and the color of his shirt, probably you may give all the data, you may give a lot of data, big data, but it is useless data. There is a very weak signal in that, if at all, right? Or maybe you can go so far as to say that if you look at the size of the shirt and the pant and the shoe, you can conclude that there's some relationship between diabetes or not, because younger people don't have diabetes. Right? And so on and so forth. So you can do something like that. And younger people tend to wear much more bright colors compared to middle-aged people. Very weak signals you can do, but there are a lot of middle-aged people who do have diabetes and a lot of middle-aged people who do not have diabetes. So your project actually may not succeed, right? The reason is then you can have a disappointment that, see, I hired all these bright people and they could find nothing. They could not solve the problem. But another way to ask this question is, was that problem even solvable? Because this is a classic example of close to null hypothesis. None of the predictors are useful. You see that, right? And that is the probabilistic nature or uncertain nature of machine learning. Another definition of machine learning is, machine learning is coming to conclusions or predicting or recognizing pattern when there is a very high degree of uncertainty. Information is not perfect, it's very uncertain information. One reason it is so useful these days in medical sciences, as you know, the big frontier these days in the next 10 years is going to be the medical sciences, the biological and medical sciences, because biological and medical data tends to be very, very squishy, soft data. The human body is insanely complex. As some of you are doctors here, physicians here, you know that they often teach you, or at least they used to, that the human body is the terra incognita. It's the unknown territory. There's too much that we don't know. There is a certain amount that we know, and research is expanding the frontiers of what we know. But there are also a lot of things we don't know. So what happens is, every time you build a model or you make a prediction, you're working with uncertain, insufficient information. There's always uncertainty. When a doctor makes a when a physician makes a diagnosis, you realize that you can go and get a second opinion and it may differ sometimes. The reason for that is they're all making that diagnosis based and weighing the information they have, which is always incomplete information. So that is something to bear in mind. And that's a frontier. That's a huge frontier for machine learning, which is why machine learning is, algorithms now are being considered an adjunct to physicians. So what people are realizing is that machine learning is very good at coming up with, let's say, 5 possible diagnoses for an illness. And they will find a common diagnosis, and they will also find likely but rare diagnosis, something that's possible or that's likely in view of this data, but that is rare and the physician may not have thought of. So it is a very good assist tool to physicians, because now they can look at the 5 and occasionally they may be surprised. They may think it's the common illness, but they may suddenly remember that, yes, actually it also seems to match these less likely diseases. Right? But I don't think it will replace physicians, because the human body still is something to understand which you need experience. There are a lot of things not there in the data. For example, the Southeast Asian body is fairly different from the Caucasian body. We know for a fact, for example, that our circulatory system, our veins and arteries are actually of lesser diameter than on average compared to the Caucasian. And it has a whole set of consequences and whatnot. So I'm told, by the way, by somebody from where, I don't know. So that's that. The physicians amongst here, I suppose, Patrick, would you agree with that? And today, do we have Sukhpal? Sukhpal, are you there? Would you agree with what I said?
Yes, sir. There's actually a field called precision medicine that's slowly emerging. So what it does, sir, is it tries to take the human body not as like in totality, so down to the genomic level. They try to look for the proteins that are more present in your body, specific.
Interesting.
Yeah, all the medicines that would target those specific proteins in your body. So like now, right now, most medications or antibiotics are just by convention. So if I tell you you're going to take antibiotics, you already know that it's going to be about 2 to 3 times a day, 7 to 10 days. You already have an idea, because that's just a convention. But precision medicine would be based on your genomic structure. We'll be able to use a computer algorithm to target the correct therapeutic window, so that you're not overdosing or underdosing. So ideally, we're trying to get to that point, but most of the things that are happening now are just the level of understanding what's happening. Maybe the conversation will be in the next generation, or might be faster. Depends on how quickly it's been taken up by the scientific community. Yeah, it's very exciting times.
Nice. All right, guys. So I'm done with the classical methods of clustering. Next time, I'll teach you one of the much more modern methods of clustering that you don't find in textbooks, or the usual textbooks, the normal machine learning textbooks, but actually is quite a bit used. And I use it actually quite a lot. And they are based on they're called density-based clustering methods. We'll talk in particular about dbScan and dental. So let's keep it for the next time, because I think we already seem to have quite a bit of conceptual overload here, a lot of things to absorb. So please review chapter 10 of your textbook. It contains dimensionality reduction and clustering. Just focus on clustering. The first part is, I believe, dimensionality reduction, which you can skip over and just do clustering. And that will be a very good review of what we have talked about here. So do that, guys. Tomorrow, next time, this Saturday, we'll do some labs on clustering. By the way, are all of you able, is it convenient for you guys to attend the labs? Right? I also post the recording of those labs.
Saturday is fine.
Saturday is fine, okay. So remember, Saturday at noon, we'll meet in my private WebEx room. And then we'll go over the labs, clustering labs. And next Monday, I'll do density-based clustering. And if time permits, I'll do dimensionality reduction. And that would be the end of the workshop. And the Saturday following that, I'll take it for helping people and maybe do an example of dimensionality reduction.
Okay.
Close the recording. That is a recording that's going on.
Asaf, I just wanted to make an announcement.
Go ahead.
Guys, please take the quiz. I think other than Patrick, I don't seem to see anyone have taken that. So please do that before you like end up the class.
Prachi, I think